uh, session, and the first talk will be by Shriharsh Tendulkar from Tata Institute of Fundamental Research, Mumbai, and he will be talking about multi-messenger and multi-wavelength observation in frbs. So, yes, Shriharsh, you have 40 minutes. Okay.
All
Yeah.
right, thank you so much.
Yeah.
Hi, everyone. It's a great pleasure to be here. I would like to thank the organizers for inviting me and also for making this online talk possible. I'm really sorry that I could not be there in person. I would have really loved to, but I'm detained otherwise. All right, so today I'm going to tell you about fast radio bursts, some of the recent advances that have been made in this very rapidly changing field. And particularly, I want to emphasize the importance of multi-messenger and multi-wavelength observations in trying to understand fast radio bursts. So the telescope which you see in the title slide is called the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, which is one of the most prolific detectors of fast radio bursts. And a lot of the results I'm going to talk about are from that telescope. And obviously, it is not a single person effort. So this is the CHIME team with a small but growing contingent at TIFR and NCRA. Our group is working on that quite a bit. So let me talk about fast radio bursts. So if you had sensitivity to radio wavelengths, you could see random flashes of light coming from different directions in the sky. Sorry, could I ask the organizers to mute the microphone, please? I'm getting an echo. Thank you. All right. So fast radio bursts, as the name suggests, are very short, bright flashes of radio light. Some of them seem to repeat. They last only about a millisecond, and they're not rare. There are about 800 of these every day in the entire sky, right, at thresholds detectable by our regular telescopes. And we know that they're coming from extragalactic distances. The first clue about their extragalactic origins is that we get a very high dispersion. What is dispersion? It is basically a different speed of light, a speed of light differing at different wavelengths. So if you see this plot here, this is called a dynamic spectrum or a waterfall plot, and it is plotting the intensity as a function of frequency and time. So frequency is on the vertical axis and time is on the horizontal axis. And you can see that this burst arrives earlier at high frequencies and later at low frequencies. And the shape of this curve is very well understood. It goes as frequency to the -2. And the total magnitude of the delay from the high frequency to the low frequency is proportional to the dispersion measure, or the dm. And that is simply the integral of the electron density from the source to the observer. So you go along the line of sight, and in essence, you're counting each and every electron that the light wave encounters from the source to the observer. Now, this dm is not known a priori, and that makes it a computationally expensive search. So in order to find an FRB, you basically have to integrate the intensity over frequency, but you go along different possible dispersion measures. So you search in dispersion measures, integrate the intensity over frequency, and what you get is a time profile, which you see up on the top, in the top panel of the plot, and you search for a burst. If you don't find it, you go to the next dm and so on. And because there are a lot of different dispersion measures, it becomes a very computationally expensive search. Now this dm, because you're counting electrons, it's also a proxy for distance after you subtract what the Milky Way can contribute and after you account for how electrons are distributed in the universe. And that was our first clue that FRBs are extragalactic. So on the left-hand side plot, I'm showing you the electron distribution model of the Milky Way. This has been estimated from various sources, but it basically gives you a top-down view of the electron density as a function of position. And so the Earth is somewhere at a y-axis, y-coordinate of 8 kiloparsec in this model. And if you give me any line of sight, I can integrate this model and say the Milky Way can contribute only so much dispersion in that line of sight, right? And so if you look at the plot on the right hand side, this is a plot of dispersion measure on the vertical axis versus galactic latitude on the horizontal axis. So -90 is the galactic south pole, 0 is the galactic equator, and +90 is the galactic north pole. And you can see all the dark blue points are have a very nice envelope, and that is basically, those are all the galactic pulsars, and the envelope is the maximum dispersion measure that the galaxy can contribute in any given direction. And what you see are that these red points, the red circles, are FRBs, which have dispersion measures which are far higher than what the galaxy can contribute. Note that the vertical axis is in log scale, so this is a very substantial change in dispersion measure. Now, if you go outside the galaxy, the electron density reduces by a factor of by 2 orders of magnitude or so. So, in order to accumulate the same amount of DM, you have to go much farther away. You have to go to gigaparsec distances to get the same kind of dispersion measures. And this was confirmed by actually pinpointing fast radio bursts, finding their host galaxies, and then measuring their redshift. So by now, we have about a dozen FRBs where the redshifts have been measured, and I'm just showing you a few of them. The first one was localized to a dwarf galaxy with a redshift of 0.2. The record holder right now is a redshift of 0.9 something, which I've not included. But there is one notable one, which is a repeating FRB in a globular cluster in M81, which is only at 3.6 megaparsec, which is very nearby. Now, most FRBs, since they come from cosmological distances, can serve as cosmological probes, right? Because they are polarized radio waves and they're interacting with every electron and every magnetic field that they traverse through. So if you have turbulence, if you have intervening halos, you'll get scattering, which you can measure. You can measure the baryon distribution. You can do some sort of a tomography of the universe. And if you have a lot of FRBs at high redshifts, you could measure very precisely when helium-2 reionization happened and how it happened. Because of the polarization and the Faraday rotation and so on, you can also use FRBs to measure magnetic field distributions. You can measure magnetoionic plasma around the FRB source and also in the intervening medium, and allow you to map magnetic fields in the universe. And the holy grail of FRBs is that you could try to find a gravitationally lensed FRB, and with that you can measure time delays to exquisite precision, to 1 part in 10 to the 13 or 1 part in 10 to the 14. So you're measuring, the age of the universe accurate to microseconds, not the age of the universe, but the travel time, which is typically billions of years, accurate to microseconds, which is fantastic, right? But before we do that, we have to separate out what properties of FRBs are intrinsic and what properties of FRBs are due to the propagation effects. And to understand that, it's a huge challenge. We don't know what FRBs are. There are about 70 different models of what FRBs can be. We set up this FRB theory catalog for a while, which lists just all the possible FRB theories and what their observational effects are and so on. Now, FRBs, because they have to be visible from gigaparsec distances, are 10 to the 12 to 10 to the 13 times brighter than even Crab giant pulses. So Crab giant pulses are extremely bright and extremely luminous. FRBs have to be a trillion times more luminous than these Crab giant pulses. So what can it be? Most of these models involve some sort of magnetars, because you need a compact object and you need a strong magnetic field to hold that much energy and release it in a millisecond time scale. So one of the common models is that there is a magnetar flare. This has been associated for a long time, and you have some sort of a magnetic field reconnection or a star quake happening on that event. You can have a neutron star binary, so you have a merger of a neutron star binary or a neutron star black hole binary, and that produces a fast radio burst. There are other more exotic models as well. Now you'll notice that some of these models can happen only once. So they're cataclysmic models. A merger of a neutron star binary will happen only once, whereas a magnetar reconnection event can happen multiple times. And so those can lead to repeating FRBs. And we see a fair fraction of repeating FRBs. There are some positions in the sky where you get bursts with almost the same DM. Many of them will repeat thousands of times. Others we have not seen to repeat despite 10 to thousands of hours of observations. Now the question is, are these different populations, or are they different ends of the same population? So I've drawn this cartoon diagram, and on the x-axis is a rate parameter, on the vertical axis is some sort of a population, and you could have two possibilities, right? One is this green sort of population where you have on the right hand side very frequent repeaters which repeat very often, and we see them as repeaters. But on the left hand side, you can have rare repeaters. Maybe they emit one burst every 10 years. Maybe they emit one burst every 100 years, which is a very short time on an astronomical time scale. But for our observations at a human time scale, it is a very long time. So maybe we see them as non-repeaters, but then in reality, they are actually repeaters. That's one possibility. The other possibility is that you have repeaters, which is this orange population on the right hand side, and then you have absolutely cataclysmic non-repeaters, which we know are just going to happen once because the object that created the FRB got destroyed somehow, right? We can't tell the differences directly from radio, at least not right now. But multi-wavelength observations will definitely be will provide concrete evidence. So in the radio, we see this. There are some FRBs which are broadband and they have single components. Now, in these plots, the dispersion has been completely removed, almost completely removed. So you have shifted the frequency channels in time so that the effect of the propagation has been removed. Now you can see the alignment of the FRB, and this is again frequency versus time. And you can see that some FRBs cover the entire 400 to 800 megahertz band. Some of them are fairly narrow band, some of them are broad. In some of them you can see scattering. But in the top, I'm showing you the broadband and single component FRBs. And in the bottom, I'm showing you some of the FRBs that have multiple components. You can see clumps of intensity, and they are narrow band. And you might ask the question, are these different? And it turns out they are. So one of our then students, Ziggy Plunis, now a Dunlap Fellow at University of Toronto, went through all of these FRBs and came up with these 4 different archetypes. Right? On the left-hand side is type 1, which is a broadband single component kind of FRB. On the right-hand side, you have single component narrow band, then you have multiple components in a spectrum. A very standard signature which we see for repeating FRBs are these multiple components which drift downwards in frequency as time passes. It's almost always downward drifting. We have almost never seen something that drifts upward in frequencies. Now, when you do the statistics, it turns out that the type 1 is most often seen from non-repeaters, and the other 3 are most often seen from repeaters. And you can quantify this by looking at the spectral shape and the intrinsic width. So on the vertical axis here, I'm plotting a parameter we call spectral running. Okay, so the top of it is when it goes close to 0, it means it has a power law-like spectrum, and the bottom is where you have a Gaussian-like spectrum. So you have a more narrowband spectrum as you go to the bottom, and you have a broadband spectrum as you go to the top. And on the x-axis again is just the intrinsic width of the FRB after you remove scattering and so on. And so the left-hand side is a narrow pulse, right-hand side is a broad pulse. Now the green points are the FRBs which we have seen to be one-off events. We have seen them happen only once. And the purple points are the first detections of any repeating FRB. And the orange points are all bursts from repeating FRBs. And you can see that there is a drastic difference in these populations. You can see the collapsed histograms on the top and on the right. And you can see that they're very, very different. And you can also see, if you look very closely in the right-hand side histogram, there is a small peak in the green histogram, which is bimodal, and which overlaps the purple and orange peaks, right? And that suggests that some of these FRBs are possibly repeating in the future. And indeed, we have found those. Like, we identified some of these as possible repeaters. And after a lot of observations, we found that they indeed did repeat. So the conclusion from this is that repeating FRB bursts are temporally wider and spectrally more narrowband than non-repeating FRB bursts. But does that mean that there are necessarily 2 astrophysical channels? And I would argue that we don't have that evidence yet. You could have burst properties that change with repetition rate. For example, if you have more rapid repeaters, you can have, maybe they have complex bursts, maybe they have also a complex magnetic field or something. And maybe the rare repeaters, they have a simpler magnetic field, they are older perhaps, and they have simpler bursts. It could be a propagation or a beaming effect. If you have a narrow beam, you'll have rarer repetition. and maybe you'll have a simpler burst because the cross section across the beam is simpler in some sense. Or if you have a larger beam, it is somehow more complicated, and then when you cut across it, you get a more complicated burst. So we don't quite know what is happening here. So there are now ongoing studies where we are trying to study the polarization differences, the differences in rates as a function of morphology, and so on. But this would help guide repeater follow-up, right? But what you would ideally like to do is to say, okay, there is this merger or a coalescence or something that happens only once, and that might have multi-wavelength counterparts, right? You might get you might get a gravitational wave event or a large X-ray burst, and that would help us figure out what exactly is happening. So with that, let me come to multi-wavelength counterparts. Now, there is this quote from Jim Condon saying that there is nothing as useless as a radio source. Okay, Jim Condon is a great radio astronomer, and he was the PI of the NRO VLA Sky Survey. And so him saying this is important because a radio source, you can say that, okay, there is something which is emitting this much energy at this location in the sky, but you don't get any spectral information. You don't really get a lot more. And our radio telescopes are extremely sensitive. They can detect pretty much anything, and it is not energetically very difficult to produce a radio source that is detectable. So in that sense, it is not very discerning. So if you want to distinguish between different emission mechanisms, what you want are the multi-wavelength counterparts. And they're also crucial in linking FRBs with other classes of transients. So are FRBs linked with GRBs? Are FRBs linked to ultraluminous X-ray sources? Are they linked to binary neutron star mergers, and so on? Right? But you can notice that the energy scales here are extremely different. FRBs have order of 10 to the 41, 10 to the 44 ergs, which is far, far less compared to 10 to the 51, 10 to the 52 ergs from superluminous supernovae and GRBs and so on. So we have been trying to look for multi-wavelength counterparts of FRBs or associate FRBs with other counterparts in some way. There are two types of counterparts. One are the prompt counterparts. So you have the explosion happening, some sort of cosmic explosion, maybe a GRB, maybe a binary neutron star merger, supernova, which is represented by the green star. And then within a few minutes to hours, you get the FRB, which is the blue lightning bolt. Now, these are easy to associate, but they're harder to find. The other possibility is that you have some sort of a cosmic explosion which leads to a stable remnant, probably a neutron star. And then after years to decades, there is some sort of the surroundings clear out, and then FRB is emitted. Now, these are harder to associate, but most of this time I'm going to talk about the prompt counterparts, but we should not forget the delayed counterparts. They also exist. Now, the first thing you notice, if you look at the observed rates, is that there is a huge discrepancy. There are about 1,000 FRBs, detectable FRBs, every day in the entire sky. There is about 1 detectable gamma ray burst every day in the entire sky. There is an order of 1 galactic magnetar flare, which is clustered in space and time, but over the year, you can average it to about 1 a day. There is about 1 binary neutron star merger that is detected in a year. This will probably change when the next LIGO cycle comes up with increased sensitivity, but right now, it's order of 1 binary neutron star merger a year. And even if you look at ultraluminous X-ray sources or high mass X-ray binary, and their outbursts are about 10 a year. So the conclusion is that there are too many FRBs in the sky, and the corollary is that very few of these FRBs will be associated with other detectable transients. So these coincidences are rare, and we need to find a lot of transients, and then we need to choose and follow up only the specific transients that we care about. We have to find the special ones. So the challenge of finding a lot of transients is that radio telescopes look at a very small part of the sky at any given moment. And there are now newer telescopes which map huge swaths of the sky, which are more successful at finding FRBs. So I'm going to talk to you briefly about CHIME FRB. The CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment. And as the name suggests, it was designed for studying baryon acoustic oscillations in the redshift range of 0.8 to 2.5. That's why it operates from 400 to 800 megahertz. And it consists of these 4 cylinders, which are 20 meters wide and 100 meters long, and they are aligned in the north-south direction. So these are paraboloid cylinders, and as the sky passes overhead, it looks only at the zenith. It is a transit telescope. It does not move, and it focuses light onto the bottom of these focal lines. You can see some of the CHIME team members standing on the focal line here. And underneath these, there are 1024 dual polarization feeds, and this gives it a very large field of view. And we operate it as a FRB and cosmology and pulsar instrument together. It simultaneously provides the backends for all of these. The field of view of CHIME is 250 square degrees, which is much, much larger than any other radio telescope which is searching for fast radio bursts. Now, CHIME was built pretty much by astronomers. So this is a range of undergraduates to emeritus professors working hands-on on the telescope. And it was a lot of fun building it. And this is how CHIME operates. Just to give you an idea, there are 1024 feeds on the antennas, and this is the Haslam-et-al map which is passing through CHIME. You can see the galaxy in radio wavelengths passing through the field of view of CHIME. What we do is we interferometrically form 1024 static beams on the sky. There are 4 beams in the east-west direction and 256 beams in the north-south direction. And each of these beams is sampled at 1 millisecond, and it produces data in 16,000 frequency channels, right? And so this is equivalent to having a video camera on the sky with 1024 pixels, but it is operating at 1 kilohertz, 1000 frames per second, and 16,000 colors. So you can imagine it's a huge amount of data. So we get 800 gigabytes of data in raw voltage per second, and that is reduced to 130 gigabits of data, intensity data, which is searched in real time to find fast radio bursts, and then we can save the small amount of data. Just to give you an idea, this is equal to 1024 of these green bank telescopes. This is a 110 meter diameter telescope. This is equivalent in sensitivity and mapping speed to 1024 GBTs. Okay, so you can imagine it's a huge amount of data and a huge. It's a very powerful tool to find transients. So CHIME has been exquisitely successful in finding a lot of interesting FRBs. So I won't go through all of these, but I will highlight that there are many papers out there which you can look up, and you can also ask questions about them. One of the very interesting things was that we detected a 16.35 day periodic activity in a FRB. We detected a lot of galactic rotating radio transients, new binary pulsars, a repeater in M81 at 3.6 megaparsec. I'll talk about the galactic FRB from a Magnetar SGR 1935 plus 2154. And there are also other properties, other papers where we discuss the population properties of FRBs. But today I'm going to focus on the multi-wavelength counterparts and the multi-messenger searches. So let me talk about how magnetars got implicated into the FRB business in the first place. So magnetars are known to emit giant flares and show a lot of bursting activity in X-rays and gamma rays. So they've been known for a while. And when FRBs were first discovered, people said, oh, this might be magnetars. And that's where the association started. And when the first repeating FRB was localized to a low metallicity dwarf galaxy at a redshift of 0.2, we asked, why is the first FRB in a low metallicity dwarf galaxy that is 10,000 times less massive than the Milky Way? If you wanted to find the youngest neutron stars, you would go to the you'd probably find it to be in a galaxy with a very high star formation rate, like R220, which is forming stars at 200 solar masses per year or something. So it turned out one possibility was that the low metallicity was also a host to long GRBs and superluminous supernovae. It was a preferential host for long GRBs and superluminous supernovae. And it came up with this idea of a millisecond magnetar model, which is a diagram shown in the bottom right, where you have a long GRB or a superluminous supernova, which is powered by a millisecond magnetar, and maybe after a decade or so, the external surroundings have cleared out and become transparent to radio waves, and this magnetar, which is still quite energetic, keeps emitting flares, which creates synchrotron emission in the magnetar wind nebula and produce FRBs. And so the synchrotron wind nebula, sorry, the magnetar wind nebula would explain the persistent radio source, which is emitting about 10 to the 38 ergs per second at the location of the FRB, which is a very nice, quite consistent model, except that it doesn't work for all repeating FRBs. There are periodicities in, there are other FRBs which don't have a persistent radio source at all. It turns out persistent radio sources are quite uncommon. And there are these periodicities. This FRB in particular has a 160-day periodic activity window. There is every 160 days there is a period of about a month or so when there are bursts, and then there is a period of no activity. Then it starts over again. This was first discovered in another FRB, FRB 18916, which had a 16.5-day periodic activity window. So every 16.5 days there will be a window of about 4 days wherein there are bursts, and then after that there is absolutely nothing. What is this periodicity? Is it some sort of orbital period? Is it some sort of a rotational period? Is it some sort of a precessional period? We don't quite know, right? But it raised the question, given that magnetars are associated with FRBs, could galactic magnetars give such bursts? And in 2020, we had our answer, and it was a fairly strong affirmative. So since November 2019, this galactic magnetar SGR 1935 plus 2154 had been actively emitting X-ray flares and bursts. So it was just rumbling around there, spitting out all sorts of X-ray flares. And on 28th of April 2020, CHIME detected a very bright radio burst. So you can see on the top panel on the left side, you can see two bursts which cover from 400 to 800 megahertz. They're separated by about 30 milliseconds. And these were the brightest radio transients that have ever been detected. It was also detected by a very small insensitive radio telescope called STARE-2, which was designed to specifically detect extremely bright flares. So it is normal FRBs and pulsars are typically detected in fluxes of Janskis or sometimes hundreds of millijanskis. This FRB was a mega Jansky. It was almost 10 to the 7 times more flux than we have ever received from anything else. So if you look at the plot at the bottom, this is the observed fluence on the vertical axis as a function of distance. So on the bottom left, you have all the pulsars that we know of, the rotating radio transients, crab giant pulses, and so on. On the top, on the right hand side, you have the fast radio bursts with their associated uncertainties in distance measurement and so on. And you can see the diagonal lines, which are lines of constant energy. And you can see the location of SGR 1935 as measured by CHIME and STARE-2, and they fall slightly short of the energetics of FRBs, which is fine, but it is not quite, it's still far enough away from pulsars. This is the first FRB from a canonical magnetar. What made this even more interesting is that there was a multi-peak hard X-ray burst which matched the radio. So there are 3 peaks in the X-ray light curve. This is from Sandro Mereghetti's paper on ISGRI counts. The gray curve shows the X-ray count. So you have 3 peaks, and the first 2 peaks match very well with the radio peaks. In fact, we now know that the radio comes about 3 milliseconds ahead of the X-rays, and that is a fairly robust evidence that the synchrotron emission mechanism doesn't work. In fact, this is the magnetic reconnection event which is happening. But there were many other X-ray bursts without radio, and there were many radio bursts without X-rays. And so we don't quite know what causes a specific burst to emit radio and X-ray, or what causes it to just emit in a particular wavelength. Recently, SGR 1935 became active again, and on 14th of October 2022, we had yet another yet another FRB from SGR 1935. Again, this was, had broad spectrum coverage and so on. It was detected by the gamma ray burst telescopes, satellites in space as well. And in fact, one of my colleagues, Yogesh Mann, was observing SGR 1935 with the Green Bank telescope, and they were staring right at the magnetar when the burst happened, and which means that the entire signal chain was completely saturated, because the signal chain is calibrated for millijansky and Jansky level bursts, and now suddenly they are hit with something that is a megajansky. So clearly, the entire system is going to be saturated. So now you might ask, does this solve all our problems? Are all FRBs coming from magnetars? So the answer to that is no. SGR 1935, like magnetars, probably don't explain all FRBs. The occurrence rate is fairly consistent with the rate of FRBs as a population. But what the kind of behavior we have seen from individual FRBs, repeaters and non-repeaters, in terms of energetics, in terms of repetition rates, in terms of periodicities, have not been replicated by any other known magnetar. So we have not seen the kinds of exotic behaviors we've seen in individual FRBs from galactic magnetars. So this question is still open. Also, FRBs don't have to come from a single channel. There can be other rare FRBs which come from other channels as well. One of the most important channels, in my opinion, is the possibility of a FRB and short GRB connection. So there are a lot of different models where you expect that if you have two neutron stars, or a binary or a compact binary with at least one magnetized neutron star, you would get some sort of a radio emission when you have a merger, right? So this can happen at the inspiral phase, this can happen during the actual merger, or this can happen from a remnant, which is post-merger. And these kinds of predictions have been made even before the discovery of FRB. So Hansen and Lutikov back in 2001 predicted that there should be some sort of a radio emission at the timescale of a few seconds. Shirkov and Posnov in 2010 proposed radio precursors for binary neutron star mergers, and this is before FRBs became an established field. So you can see this diagram on the top right from Antonia Rowlinson's paper, where there can be expectations of radio emission up to 10 seconds before the FRB, or thousands of seconds after the merger of a binary neutron star. So there are a lot of different models about where and how FRBs can form before, during, or after compact binaries involving neutron stars. But there can be differential beaming. Maybe the GRB comes in one direction and the FRB goes in another direction. So we detect the GRB but not the FRB, or vice versa. There can be a lot of plasma around the environment which prevents the FRB from reaching us. So there are different ways in which we can prevent the joint detection of FRBs and GRBs as well. We have been trying to find prompt counterparts of FRBs and GRBs for a while now. So this is a paper. We did some work with AstroSat. We looked at cadmium zinc telluride imager data, and we looked for all possible FRBs. We got only upper limit. So we have fluence limits of about 10 to the minus 7 to 10 to the minus 6 ergs per square centimeter on all these FRBs. So we did not. So this obviously is not very constraining. But if you have actual detection, that would be worth the effort. So we continue to make these efforts with different observatories in order to find gamma ray counterparts or X-ray counterparts of FRBs, so that we can actually constrain the emission mechanism. One could also ask at the inverse question: given a GRB, can we find an FRB? And many people have tried this. So Keith Bannister, Divya Palaniswamy, and others have followed up GRBs with small radio telescopes. So as soon as a GRB comes, they can quickly move the telescope and start observing that location and look for bursts. And this usually happens a few minutes post the burst, because even a small radio telescope is about tens of meters in size. So rotating it takes a little bit of time. With new phased arrays, you can have faster beam switching, so you can steer the beam electronically and you can get a few seconds latency. But with chime, what we have tried to do is that we can put limits on FRB like transients before and after the GRBs. Because GRBs occur randomly in the sky, some of them will occur before the transit, some of them will occur after the transit, and we can get a fairly good idea of what sort of limits we have. So one of my students, Alice Curtin, she searched for FRBs before and after GRBs in the first year of chime's operation. And it turned out that we have no coincidences, but we can put fairly interesting limits. So on the top left is a plot of fluence limits as a function of time around the GRB. So when the GRB is not in the primary beam, you get fairly high limits, about few thousand Jansky or a few kilo Jansky scale. But when the GRB is very close to the primary beam, you can get very deep limits. The red star here shows the time of the GRB itself, and the arrows show upper limits which we can put at that location in the sky before and after the GRB. Now, for a single FRB, this is not very constraining, but you can combine a lot of GRBs together and try to get a sort of envelope of what constraints you can put. So the plots on the bottom show the radio to X-ray fluence ratios which we can constrain for long GRBs and short GRBs. Now these put limits on the radio efficiency of short GRBs to be somewhere less than 10 to the minus 3 to 10 to the minus 4. For repeating FRBs, we can also do focused observations. So we have done simultaneous radio and X-ray observations of these repeating FRBs with telescopes like XMM, Chandra, and NewStar. And you can actually get fairly deep limits. You can put fluence limits of 10 to the minus 10 to 10 to the minus 9 ergs per square centimeter. And at the distance of FRB 180916, which is what we call R3, which is about 150 megaparsec, the energy limits which we are putting is about 10 to the 45 ergs, which is far greater than the FRB energy, but it is also comparable to a Magnetar giant flare. So the SGR 1806 minus 20 giant flare in December 2004 had about 10 to the 47 ergs. It was the brightest giant flare we have ever seen. And to compare that, the SGR 1935 burst in 2020 was about 10 to the 39 ergs. So we would not be able to detect this. So we need more nearby repeaters to improve these constraints. We have had similar efforts on repeaters. You can do simultaneous observations in radio and in optical, and we can get limits. None of these limits are yet constraining, but if you have very high FRB fluences, then the ratio between radio to optical can start becoming constraining. So if you go to large area surveys, which have, most of these efforts are done with high-speed cameras, which are very specialized instruments on specific telescopes. But you can also try to do this with regular surveys, like the deeper, wider, faster survey, which has been doing coordinated observations in radio, optical, infrared, and X-rays. And there are a lot of future possibilities. So every scope, the Zwicky Transient Facility, the Vera Rubin Observatory, they're doing integration times of 10 to 60 seconds, but because they have large telescopes, you can go fairly deep in luminosity. There are, of course, challenges. You have integration times which are longer, so you're diluting your signal, and you also have to separate asteroids and satellite gleams from single frame transient. So this becomes quite challenging, but it is an effort that people are putting in for a long time. The third aspect of this search is to search for gravitational waves. So
you have 2 minutes.
Thank you. Yeah. So we have done searches for unmodeled gravitational wave events at the times of FRBs. It turns out we can exclude things which happen, things like binary neutron star mergers in the distance range of about 150 megaparsec. Now the future runs with LIGO will be more sensitive. We can go to a larger exclusion distance. And I'll note that there is a posted possible association of a gravitational wave event with an FRB, which happened 2.5 hours after the detection of the gravitational wave merger. So the statistics of that is a little bit questionable, but it is certainly a very interesting find. So the important takeaway point from here is that we need to find the nearest and brightest FRBs. We don't care about FRBs that are too far away because our gravitational wave and X-ray and other telescopes cannot find transients that are much further away, right? So we want to cast a very wide net. We can only find FRBs which are very bright, which are in the side lobes of telescopes, because that's where most of our sky area is. We don't care about the sensitivity, but we care about the sky area. So what we are proposing is to build a all sky transient radio array we call Astra. I've not updated the name here, but on this plot I'm showing the detection threshold on the vertical axis. So top is less sensitive, bottom is very sensitive, and on the right hand, on the horizontal axis is the field of view. So if you go to the right hand side, you can go to much larger fields of view. Now CHIME is operating at about 250 square degrees, but we want to go to somewhere between 10,000 to 15,000 square degrees with a much lower sensitivity. We can trade off the sensitivity for field of view and try to detect 1 to 2 ultra bright FRBs every month with sub-arc second localization. Now the challenge here is that we need to build about 2,000 signal chains. How do you deploy inexpensive analog signal chains and buffer a lot of data? So this is a lot of effort that is happening. There are also other telescope all-sky monitors which we are collaborating with, GREX at Caltech, BURST in Taiwan, and so on. And at the same time, we also want to improve the X-ray limits. So we are working on this X-ray telescope called Daksha. It comprises of 2 satellites in antipodal orbits, which has an all-sky view for X-ray transients. So it will cover 1 keV to 1 MeV in energy range with a very large collecting area. So this will be the most sensitive all-sky X-ray monitor in the world, and this will help us find gamma ray bursts, magnetar flares, and FRB counterparts. So this will be, for those of you who use Swift, this will have the sensitivity of SwiftBAT, but SwiftBAT covers only 1/10 of the sky. This will be the entire sky. So let me stop here with my conclusion and summary slide. There are significant differences between repeaters and non-repeaters, but to have a concrete evidence that they're coming from different astrophysical channels, we need to prove that the non-repeaters definitely died and will not ever repeat. And the way to do that is to associate them with cataclysmic events from other wavelengths or other messengers. Some FRBs we know come from magnetars, but also some FRBs could come from binary neutron star mergers. So this kind of multi-wavelength, multi-messenger counterpart searches are urgently needed. And to do that, we are trying to work on localizing the nearest and brightest FRBs, because those are the ones which are most likely to have counterparts. So let me stop here and thank you.
Yeah, thanks, Shriharsh. And I think we can take 1 or 2 questions. So,
okay.
Yeah, there is one question here.
Thanks, Shriharsh, for the nice talk. Just a quick question. In one of your slides, you showed that you can do these cross-correlation studies of FRBs with galaxy catalogs. What do you expect to learn from those studies?
Right. So let me go back here. So this is work done by Masood Ravandi Rafiee at Perimeter Institute. So the aim here was to cross-correlate FRBs with galaxy halos at different redshifts. And one of the things is that we don't know at that point only a few FRBs were actually pinpointed. So it would be important to know whether other FRBs which are not very well localized actually do correlate with galaxies. And because you can do redshift bins for different galaxies, you can find out the typical redshift range for your FRB sample. So it turns out that our FRB positions correlate very well with halos in the redshift 0.3 to 0.5. And that means that most of our FRBs are coming from approximately that distance, in the CHIME FRB catalog at least. So this is something to do with the sensitivity of CHIME, obviously, because we can't detect FRBs which are too far away; they would be too faint. And when you come closer, then the volume becomes smaller. So this is our sweet spot. The other thing that we concluded from that paper is that there are a small population of FRBs which have a very large host DM contribution. So the host DM contribution itself turned out to be about 400 parsec per cubic centimeter.
Okay, and then just one question.
So Shriharsh, just going along the same lines, at some point you mentioned this connection between FRBs and the galaxies, and maybe it's residing in dwarf galaxies. So with respect to the cross-correlation studies, do you know what is the bias of galaxies in which these FRBs are residing?
That's a good question. So this cross correlation was done with galaxies, with the halos themselves, not with specific galaxies. If I remember correctly, Masood basically took only the brightest galaxies in the halo.
No, that's right. But if you look at the cross correlation strength, it can also tell you about the bias of the hosts of the FRBs. And so
that's a good question.
Yeah.
I don't know the answer to that.
Yeah, because if it is between dwarf galaxies, then you should be able to see that the bias of the FRB host is low. And that you can pick up from the cross correlation.
That's true. So I will also add that so the first FRB was localized to a dwarf galaxy, but it turned out that was extremely atypical for FRBs. And now that we have a dozen or so FRBs that are localized, they seem to come from all sorts of galaxy morphology. So we have had FRBs in the outskirts of sort of elliptical-ish galaxies, FRBs in the middle of spiral arms, all sorts of things.
Okay. Yeah, I mean, getting the average bias is useful. So
yeah. Of course, it is useful. No, that makes sense. Thanks.
Yeah. So I'm afraid, Shantanu. So we have to move on. So thanks, Shriharsh. I mean, for a very wonderful talk.